We are going to begin the final chapter of the course. And as we begin to talk about vector spaces and talk about a basis for a vector space, this is not actually a new concept. We've actually, without realizing it, encountered vector spaces several times already over the course of this class. So, what is a vector space? A vector space is a set that behaves like Rn, a set that behaves like the set of n-dimensional vectors. It behaves like Rn even though it's not equal to Rn. So for examples of vector spaces that we've already encountered throughout this course, for example, suppose that we're dealing with a slanted plane in three-dimensional space, the kind of plane that you would get if you looked at the span, for example, of the two vectors 1, 0, 1 and negative 1, 1, 0. A slanted plane in three-dimensional space is not equal to R2, but it resembles and it behaves like R2. It behaves like the set of two-dimensional vectors. So this slanted plane would be an example of a vector space, something that looks like R2, something that acts like R2, even though it's not strictly speaking equal to R2. Other examples of vector spaces, the null space of a matrix, also known as the kernel of the associated linear transformation, those are vector spaces. For example, when we found the null space of this matrix A back in a previous lesson, we saw that this null space could be understood as the span of a single vector 1, minus 2, 1. So this null space kind of resembles and behaves like R1. The set of one-dimensional vectors. It behaves like R1 because it's spanned by a single vector. It looks like R1 because it resembles a line. So this null space behaves like R1 even though it's not strictly speaking equal to R1. All the column spaces that we've calculated are also examples of vector spaces. For example, in this video, when we looked at the column space of this matrix, we saw that the column space of this matrix was spanned by two vectors, the two pivot columns 1, 4, 7 and 2, 5, 8 of the matrix. So this column space resembles R2. It resembles R2 because it is spanned by two vectors. So this guy looks like a plane within three-dimensional space. So this guy resembles R2. It resembles the XY plane. It behaves like the XY plane, even though it's not strictly speaking equal to the XY plane. Another example of a vector space that we've worked with up to this point, anytime you calculate the eigenspace associated with an eigenvalue, every eigenspace is an example of a vector space. For example, in our diagonalization video, we found an eigenspace corresponding to an eigenvalue of lambda equals 1. And in this case, the eigenspace was spanned by a single vector. So this eigenspace resembles R1. If you look at the eigenspace graphically, it's going to look like a straight line. It's going to look like just the x-axis, the set of one-dimensional vectors. So this eigenspace is a vector space resembling R1. And the same thing was true with the other eigenspace that we calculated later on in this example. The eigenspace corresponding to the eigenvalue -2 for this matrix was spanned by two vectors. So graphically, this eigenspace looks like a plane, and it resembles R2. It resembles R2, it behaves like R2, even though it's not, strictly speaking, equal to R2. Finally, another vector space, a kind of strange vector space that we have encountered before in algebra, is the set of polynomials of a certain degree, polynomials of degree less than or equal to n. We'll see later in this video how it is that the set of polynomials can be considered a vector space. Now, when you're dealing with a set and you're trying to determine is this a vector space or not, you should understand vector spaces as being characterized by three main properties. And the first property of a vector space is that you can take two elements in the vector space and you can add them together or you can subtract them. And when you add the two elements in the vector space, slash when you subtract the two elements in the vector space, the result of that is also in that same vector space. So to see this property in action, for example, in R2, this property shows up as the fact that you can add together a pair of two-dimensional vectors, and the result of that is going to be another two-dimensional vector. So you can add two elements of this set together, and then the result is still in this set. You can add together a pair of two-dimensional vectors, and the result is still a two-dimensional vector. You can see this property show up in the span of a pair of vectors. If I call the first element W1, which is some combination of this first vector, I'll call it V1 for short, and this second vector, I'll call it V2 for short. And I have another element in the vector space, which is some other linear combination of V1 and V2. If I add those elements together, then I can essentially combine like terms. And I can think of this as the numbers C1 plus D1, quantity times V1, C2 plus D2, quantity times V2. So if I start with two elements in the span of these vectors, then the result is still in the span of those two vectors. It's still expressible as a linear combination of these two vectors. Let's see this property as it manifests in the null space of a matrix. If I start with two elements in the null space, W1, W2 in null space, meaning that if I apply whatever matrix to these vectors, I get 0 as the result. What happens when I add these two vectors together? Well, when I apply the matrix A to W1 plus W2, and I distribute the matrix A to each piece, then the first quantity becomes 0, the second quantity becomes 0, and the result of adding those two zeros together is also 0. And so that means that the sum of these two elements is also in the null space. So starting with two elements in the null space, adding them together, I just got another element that still is in the null space. Column space. If I start with two elements in the column space, there are vectors, called it x1 and x2, so that ax1 produces w1 and ax2 produces w2. If w1 and w2 are in the column space, then that means it's possible to produce those vectors as outputs from my matrix. Now if we consider what happens if we apply the matrix A to the sum x1 plus x2, and I distribute that matrix to each piece of the sum, ax1 is equivalent to w1 and ax2 is equivalent to w2. So what I have just done is produced the vector w1 plus w2, which means w1 plus w2 is in the column space. So I took two elements in the column space and added them together, and the result was still in the column space. To see this property at work in eigenspaces, suppose that we have two eigenvectors, v1 and v2, corresponding to the eigenvalue for this space. Let's just call it lambda. What this means is that A applied to v1 is equal to lambda times v1, and what this means is that A applied to V2 is equal to lambda times V2. So now let's see what happens when we apply the matrix A to the sum of these two eigenvectors. If I apply the matrix A to the sum of these two eigenvectors, v1 plus v2, if I distribute that matrix A to both pieces, then AV1 becomes lambda V1, AV2 becomes lambda V2, and then that lambda can be factored out. So the sum of these two vectors has the property that when you apply the matrix A to that sum, the result is lambda times that sum, and therefore the sum is also an eigenvector corresponding to lambda. The sum is also in the eigenspace for lambda. And finally, to see this property manifest in the context of polynomials, if I have two polynomials of degree less than or equal to 3, for example, if I have a pair of cubic polynomials, then when we add them together, the result is also going to have a degree less than or equal to 3. If I have, for example, 3t to the fourth power plus 2t plus 8, and I add that to 5t to the fourth power plus 6t squared plus 3t minus 9. If I add those results together and combine like terms, what results from that is just another cubic polynomial. So I started with two elements in this set, the set of cubics. I add them together and I get another element in that set, another cubic. So this is the first property that characterizes a vector space. This is the first property possessed by any set that quote unquote behaves like Rn. You can take two elements in the vector space, you can add them together, you can subtract them, and the result is still in that vector space. The second property that's possessed by vector spaces is that if you scale elements in that vector space, then the result is also in that same set. So for example, in R2, this looks like if you take a two-dimensional vector and you scale it by whatever number, the result of that is still just a two-dimensional vector. So by scaling something in the set, you've ended up with something else that's also in that same set. As far as span is concerned, if you have the span of a pair of vectors and you start out with an element W in that set of vectors, calling this first guy V1, the second guy V2, if I then go ahead and scale that vector W by another number, then that really just changes the scalar multiples on V1 and V2, but the end result is still a linear combination of those two elements. So this set is also what we would call closed under scaling. If you scale an element in the set, the result is also in the set. Null space as well is closed under scaling. If you have a vector v in the null space and you scale that vector v by a value, you can just factor that scalar out. And if you scale the zero vector by any value, the result of that is the zero vector. So that means CV is in the null space as well. Same thing is true for column space. Column space satisfies this property that if you have a W in the column space, meaning that A is capable of producing this vector, it's possible to produce this vector W by applying the matrix A to some vector X in the domain. If I wanted then to produce the vector C times W, all I would have to do is input C times X. So column space is closed under scaling, and likewise eigenspaces are closed under scaling. If I have V in the eigenspace, and if I think about what happens when I apply the matrix A to some scalar multiple of V instead, I can factor that scalar out and apply the matrix A just to V, so I get C times lambda V. So that's lambda times CV, and that means that CV is in the eigenspace as well. And as well, the set of all cubics has this property also. If I take a cubic polynomial and I scale it by some value, for example, if I take the polynomial t cubed minus 4t squared plus 3t plus 9, and I scale that by the number 5, the result is also a cubic polynomial. The final property possessed by any set that can be called a vector space is that the vector space contains a zero element. So for example, in R2, the zero element 0, 0 is certainly contained in the set of two-dimensional vectors. In the span of 1, 0, 1 and minus 1, 1, 0, the zero element is contained in that span because the zero vector can be constructed by combining 0 times v1 and 0 times v2. So the zero vector is a linear combination of v1 and v2, which means that the zero vector is in the span. In null space, the zero vector of the domain is always in the null space of a matrix, as we've observed earlier. If you plug in the zero vector of the domain to a matrix, what results from that is always the zero vector of the codomain. And that means the zero vector of the domain is in the null space. And the same equation actually is proof that the zero vector of the codomain is in the column space, because this equation also shows that A is capable of producing the zero vector of the codomain. When we write down the eigenspace corresponding to a matrix, our process for that is to write down the eigenspace as a span of a set of eigenvectors. And as we've already noted, the zero is always in any span of a set of vectors because the zero vector can always be produced by just applying zeros to each vector in your set. And in the set of cubic polynomials, the zero element would just be the zero function, z as a function of t equaling 0 at all times. The zero function counts as a polynomial of degree less than or equal to 3. So the zero function forms the zero element in this set. So those are the three properties possessed by any set called a vector space. A vector space is a set that resembles Rn. What do we mean when we say it resembles Rn? Well, in some sense, it visually resembles Rn. Often when you graph the set, it looks like a line or a plane, or it looks like three-dimensional space, etc., etc. You can also investigate three properties possessed by vector spaces, namely that they're closed under addition. If you add two elements in the space, the result is also in that space. They're closed under scaling, and the space contains a zero element. The zero element is in the vector space. Those are the three properties that you're checking when you want to determine if a set is a vector space or not. Now, when you have a vector space, there is a special set called a basis. And a basis for a vector space is a set of independent elements that spans the space. Once again, this is new language for a concept that we have been using many times up to this point in the class. When we found in the eigenvectors and eigenvalues lessons, when we found the eigenspace of a matrix, we expressed that eigenspace as a span of a certain set. So this set of these two eigenvectors would be what we call the basis for the eigenspace. Back in our lesson on null space, we found the null space expressed as a span of a set of vectors. This set of vectors that spans the null space is what we call a basis for that null space. Same thing is true in the column space lesson. We express the column space as a span of a set of vectors, and this set of vectors would be called the basis for the vector space, and so on and so forth. Basis is a set of independent vectors that spans your vector space. For some additional examples, if you're thinking about the set of cubic polynomials, a basis for that set of cubic polynomials can be found by looking at the power functions 1, t, t squared, and t cubed. And the reason why this set forms a basis for the cubic polynomials is because these functions are independent. You cannot find any one of these functions by linearly combining the others. And every cubic polynomial has the form some number times t cubed, some number times t squared, some number times t, and some number times 1. So these functions are independent from each other, and every cubic polynomial in the set can be found in terms of a combination of these four functions. For the folks who have taken differential equations, you've also encountered vector spaces and bases within that class when solving linear homogeneous differential equations. For example, if you're trying to find all the functions such that y double prime minus 7y prime plus 6y equals 0, you start that process by trying to find a pair of independent functions, y1 and y2, two independent solutions to this equation. For example, here I think the solutions might be e to the 6x and e to the 1x. Once you've found two independent solutions, these form a basis for the vector space of all other solutions. So every other solution can be expressed as a linear combination of these two independent starter solutions, y1 and y2. So this is also a concept that you might have encountered if you've taken differential equations before now. That concludes today's material. In today's lesson, we learned about the definition of a vector space, and we learned about the definition of a basis. And these two definitions are basically meant to capture a pattern of behavior that we've seen in many instances throughout the class up to this point. A vector space is a set that looks like or behaves like R2 or R3 or R4 or something of that nature. A set that behaves like the set of n-dimensional vectors, even though it's not strictly speaking equal to that set. Vector spaces are characterized by three main properties. One, they're closed under addition. So you can add or subtract two elements in the vector space, and the result will also be in that vector space. And this is meant to emulate the fact that if you add together a pair of two-dimensional vectors, the result of that is also a two-dimensional vector. So this is a quality of R2 that we would also see manifesting in any other vector space. The second quality of a vector space is that it's closed under scaling. You can scale an element in the vector space, and the result after the vector has been scaled is still inside that vector space. This is meant to emulate the property that if you take a two-dimensional vector, for example, and scale it, the result is still a two-dimensional vector. It's still in R2. And the final property of a vector space is that it contains a zero element. And this is meant to emulate the fact that in R2, for example, R2 contains an element, namely the zero vector, 0, comma 0. And if you have a vector space, then you can talk about a basis for a vector space. A basis is just a set of independent elements that spans the space. So for example, when we talked about column space, the pivot columns of A form a basis for that space.